Hi guys! Our today's lesson is going to be the second part of our first section in chapter 12, which is our lines that intersect circles. This is part 2. And for today's objective, we're going to basically be talking about all the properties of tangents, okay? All the properties of tangents that we need to solve problems. All right, so we've got a couple other pieces of information in here as well. First of all, let's take a look at this. How do you know if two circles are congruent? Well, two circles are going to be congruent if and only if they have equal radii, right? If the radii lengths are equal or congruent, then your circles will be congruent. So because these both have 5, that means the circles there are congruent, and that's how we would say it. Circle A is congruent to circle B, and the reason that is because their radius lengths are the same. All right, the next concept we talk about is this concept of concentric circles. Concentric circles are basically a circle inside of a circle. And you have to have at least 2, right, to have a circle inside of a circle. But you can have a whole bunch, right? It's like a bullseye. Really, it looks like a bullseye. But the thing is, they must have the same center. Okay, so whether it's like this with just 2 or this with a whole bunch, they have to have the same center. Okay, the next concept here is the concept of tangent circles. All right, tangent circles. Basically, what this is two circles that are tangent to each other, which means, remember the word tangent. The tangent means a tangent line touches a circle in one point, right? Tangent circles are going to be circles that touch each other in one point. So, two coplanar circles that intersect the same point are called tangent circles. And there are 2 types of tangent circles. There are internally tangent circles and there are externally tangent circles. Internally means that you have one inside of the other. Their center points are not going to necessarily be the same. That's why you see 2 different centers here. But they touch each other at one point. So it's a little circle inside of a bigger circle where they're actually touching in a point. So those 2 circles are what we call internally tangent circles. If the circles are outside of each other, touching at one point, they're called externally tangent circles. Okay, so that is the concept of tangent circles, and we have 2 different types. Internally, one's inside of the other. Externally, they're outside of each other, touching in a point. Now, we go to the next concept, and we talk about common tangent lines. Okay, common tangent lines. And once again, we can have 2 types. Okay, there are 2 types for this as well. Now, a common tangent is a line that is tangent to 2 circles at the same time. So look at this picture right here. I have two circles here, and this line right here is touching both circles at the same time, and this line is touching both circles at the same time. But if you notice, they're crossing along the outsides. They do not cross inside. This picture, they're crossing in between. This, they're crossing on the outside. This is what's called a common external tangent, okay? So the circles themselves are not tangent. These circles are not touching each other, all right? They are not touching each other. But the lines here are touching both circles. So they have a common external tangent line. As opposed to this one, where they're crossing in between. That's called a common internal tangent, right? Now, the question is, can you have circles that are tangent and have common tangent lines? And the answer to that is yes, right? I'll do a quick picture down the bottom here so you see what I'm talking about. I can have 2 circles that are touching each other, and they can have common tangents. I can have one that crosses in between. That would be a common internal tangent. And I can have some that cross on the outside, right? They could actually cross outside. So I could have one out here, and that would be a common external, and this would also be a common external. So in a picture like this, where the circles are tangent to each other, you can have 1 common internal going on the inside and 2 common external tangent lines on the outside. But the circles in this picture are tangent to each other. And you can also have this scenario too, where you have the one inside of the other and they're touching in a point. Now in this picture, I'm only able to have 1 common external. I can't make one that's going to cross in between the 2 of them and touch both circles in one point. It might touch the little one in one point if I cross through here, but it's not going to touch the other one in one point. For the other one, it would be a secant. So this one can only have 1 common external tangent, whereas this type could have 2 common externals and a common internal, okay? So you can have tangent circles have common tangent lines, right? But the circles don't always have to touch to have common tangent lines. In this case, these circles are not tangent to each other, but they do have common tangent lines. All right, let's look at the answers to this question. It says we want to figure out what the answers are. Name a line that satisfies the given description. All right, so we want a line that is tangent to circle P, but not to O. Something that skims along the outside of P, so look at P, look at the lines that are skimming along outside of P, but it is not tangent to O. Well, look at this line right here. This line right here, it's skimming along the outside of P, but it goes through O there. So it would be tangent to circle P, but not to O. So that would be line OB. Line OB would be the answer here. This one is also a tangent, right? This one is also a tangent, but this one is tangent to both. It's touching both of them on the outside. So the next question says, find the common external tangent to circle O and circle P. There should be a P there. All right, so that line, as we just talked about, would be CD. That is a common external to both. It's crossing on the outside. As opposed to the last question, which is asking you to find the common internal tangent. The common internal ones are the ones that cross in between. So this one right here crosses in between the two. It touches circle O and it touches circle E, both each at one point. Okay? So that line would be line AE there. I know this can be a little bit confusing here. We're going to do some more problems with this. So let's go on to the next part. All right, so we're going to get into this a little more here. Tell whether the circles are externally tangent, internally tangent, or not tangent. So again, what they're asking you for there is, do the circles touch in one point? If they touch in one point, are they inside of each other, outside of each other, right? Or actually, this would be outside of each other, inside of each other, or they're not tangent at all. So look at this. Do these two circles touch each other in one point? Well, they touch here and they touch here. Is that one point? No, right? No. So for this answer here, for part A, these circles are not tangent. Okay, so the circles are not tangent. Let's look at the next one. Are these circles tangent? Do these circles all touch in one point? Yes, they do. Okay, so the question is, are they internally tangent or externally tangent? Look at the circles. They're all inside of each other. So that means the circles there are internally tangent. So they are internally tangent circles. All right, look at this last one. Do all of these circles touch in one point? Are all of these circles touching in the same point? No, they're not. So we would say again that they are not tangent. The circles are not tangent to each other. Okay, now we're going to do part B. Tell whether the line is a common internal tangent, a common external tangent, or neither. So is this line common to both circles? Is it touching both circles in one point? Yes, it is. And it's going along the outside. So we say that is a common external tangent. That line. So we're talking about two different things here. Part A was all about, do the circles touch each other at one point? And part B is, how about that line? Is that line touching both circles at a point? Yes, it's touching one at this point and one at this point. So that means it's a common external tangent. How about this one, right? Here's the line here, skimming along the outside, but it's, again, outside, right? It's going along the outside of the circles. So that is what we call a common external tangent. It's another common external tangent. Internal would be, again, crossing somehow in between the two. And the last one, you know, that line is not tangent to all of them. So once again, it's neither, right? It's neither. It's neither a common internal or a common external. Neither. Not a tangent line. Not a tangent line. Okay. Actually, we say, I'm going to correct this a little bit. It's not a common tangent. So it's a tangent to the one, but not to all of them. So we can say it's not a common tangent. Okay. All right, let's go into this next concept. This next concept is super important. We're going to use this a lot. This is the concept that whenever you see a tangent line and a radius, there will always be a right angle, always. Now, you may not have one written there, but you are going to always write one there. Okay, so if there's not one written for you, you need to put it in. Anytime you have a radius and a tangent, it will be perpendicular. If a line is tangent to a circle, then it is perpendicular to the radius drawn at the point of tangency, right? So the radius is perpendicular to a tangent. That is super important, okay? And if there's not a little right angle there, you've got to add one. And the converse is also true. So basically this just says if you have a line that's perpendicular to a radius at a point, right, then the line, that must be a tangent line. So they're just saying in this case, it's kind of the opposite. If you know that it's a right angle here, then you know automatically that that line is a tangent. All right? We're going to mainly use this concept here. All right, so let's take a look at these three examples down the bottom. Okay, so this is where we're going to be doing some application of our tangent rules. All right, so let's take a look here. What you are seeing here is you are seeing a radius then you are seeing a tangent, okay, right here. So that means that there's a right angle right there. All right, so I have two sides of a right triangle. So I have 12 squared plus 20 squared equal to x squared. I'm going to use the Pythagorean theorem here. So that's 144 plus 400 equals x squared. We get 544, and we have to simplify, right? We have to simplify that. So let's take a look. We've got to break down the square root of 544. All right, let's break that down. Let's break that down. So we've got what numbers go into it. Now, this is where you guys could use your birthday cake method to break it down, or you could simply just figure out what is the biggest perfect square that goes into it. To save time, I'm going to do this. 16 and 34 are the numbers. So the square root of 16 is 4, and root 34 does not break down. Okay, that does not break down. So 4 root 34 is our answer there. All right, let's go to the next one. Now remember, this one's a little tricky, okay, because I don't have all of this. I know the whole thing is 14 and plus that y. I could add these two together, right? That will be added together to get the whole thing. But I don't know what that is. I don't know what this is. So at this point, I can't use Pythagorean theorem. But I do know one super important thing, and that is the fact that every radius is the same length. So if this is 14, then x is also 14, okay? So let's set up the Pythagorean theorem. I'm just going to call this whole thing, let's call that C, because in Pythagorean theorem, that would be our C. And remember, we have a radius to a tangent, so that means this must be a right angle. Every time you have a radius to a tangent, you get a right angle. So let's set this up. 14 squared plus 28 squared equals C squared. Okay, I'm going to find out the length of the whole thing, and once I do that, I'll be able to take that number and subtract 14 to get the y there. All right, so let's solve this. You've got 14 squared, which is 196, and you've got 28 squared, 784, all equals C squared. That works out to be 980, right, equals C squared. And now I have to take the square root. And again, to save time, I know that it's going to be 196 times 5 equals our C value. Now, the C works out to be 14 root 5. Okay, now, this can be a little tricky, right? Because you have to find y. Your C value here is 14 root 5. Okay, so we need to take a look at this and say, all right, I got to find out what this is. Now, guys, you have to be careful here. All right, I want you to be very careful here. 14 root 5 is the whole thing. Minus the 14 would give us the value of y. Now, you are going to be very, very tempted in this problem to tell me that 14 root 5 minus 14 is root 5, and that is not the case, okay? You actually could leave the answer just like this, because if you remember, when you are combining radicals, they have to actually be the same radical. There's no radical over here to combine that. They would both have to be a root 5 in order to put them together. The only other thing you could do, right, is to make them be a decimal. So what is 14 times the square root of 5? Well, I have 31.3 there. So this value here is 31.3 minus the 14 would give me y. And as you see there, you get an answer of 17.3. So the y value is actually equal to 17.3. Now, is that worth root 5 if you had just done 14 root 5 minus 14? No, right? That's not what you would have gotten. Okay, because if you did 14 root 5 minus 14 and you told me the answer was root 5, that's not worth 17.3. That's only worth 2.2. So you see, you can't just subtract them. You have to convert it to a decimal, then subtract the 14 in order to be able to get that y value there. So that y is actually 17.3 for that one. So for this question here, we had x equal to 14 and our y value equaled 17.3. So those were our two answers for that question. All right, let's look at the last one. This last one says they already have all the numbers. They're asking you, is line CB a tangent? Is it a tangent? Okay, well, let's take a look. We don't know. If we can't, this is a radius tangent. We're trying to figure out if it is. They've already given us these numbers. So what we could do is you're really going to try to figure out, is that a right triangle? Now, you've done this before, right? We use the Pythagorean theorem to figure out if three numbers make a right triangle. If you remember, we plug them into the Pythagorean theorem, and we see what happens. Right? If they come out equal, then it's a right triangle, right? If not, it could be acute or obtuse. So we know this is 9, this is 144, and 15 squared is 225. And of course, when I add 9 plus 144, I get 153, right? That is not equal to 225. So that is not a right triangle, which means that is not a right angle, And therefore, since it's not a right triangle, that means that line CB is not a tangent. It's not a tangent. So that's a tricky concept. You're plugging in a Pythagorean theorem and see if you get a right triangle. If you don't get a right triangle, then that line is not tangent. I realize it looks it, but that's only because we made it look that way. The idea is look at the numbers. You got to go by the numbers and see what happens. When you plug it in Pythagorean theorem, you say, okay, didn't come out equal, so it's not a right triangle. If it was a right triangle, then yeah, CB would be a tangent. But it's not a right triangle, so line CB is not a tangent line. Okay? All right, let's continue. All right, we got one more super important concept for this. And this is the concept that when you encounter two tangents intersecting and meeting at a point, do you see how this line is going to be tangent? It's going to keep going and kind of go out this way, right? Let me continue that line just to show you. And this line would keep going and go out that way. They're tangent lines. But if you notice, they're coming in and they're meeting at a point. If two segments are tangent to a circle from the same exterior point, then the segments are congruent. And by the segments, I mean from here to here. That part there is equal to from here to here. That's what we mean by the segments, right? So EF and EG would be congruent to each other. Two tangents to a point are congruent. So two tangents that meet at a point are congruent. Okay, so that makes these problems easy, right? So take a look. They're all kind of the same concept. I have two tangents here, right? And it says segments in each figure are tangent. We know they're tangent because they told us they were. All right, so since they're tangent, we know that they're going to be equal. So all we have to do is set them equal to each other. X plus 3 is equal to 2x. We solve for x there, move the x over. 3 is equal to x. So that's your x value, but you're not done. They asked you to find BC. So for BC, we had to plug in to the x plus 3. So that's 3 plus 3. That BC value will equal 6 for that one. Okay, I did the next one for you again. Same idea. Two tangents meeting at a point are going to be congruent. So y plus 6 is equal to 2y minus 2. They are equal to each other. Now you need to solve for y. Bring the y this way. 2y minus y is y. Add the 2 this way. You get 8. So 8 is equal to y. Now it said to find LM. So for LM, we have to plug it in. 2 times the 8 minus 2. So that's 16 minus 2. That's 14. So the length of LM works out to be 14 there. All right, let's do another one. Again, same idea. Two tangents that meet at a point are congruent. So 5y is equal to 3y plus 4. I'm going to move the 3y over. I get 2y is equal to 4. And then, of course, divide by 2 on both sides. Y is equal to 2 there. All right, but it said to find RS. So we have to go back in and find RS. So we're going to take that 5 and multiply times 2 there. And, of course, we get our answer to be 10. So RS there is equal to 10. All right, and the last one here, again, same idea. You're just gonna set those two equal to each other. There are two tangents meeting at a point. Set them equal. Move the x over, you get x when you subtract it. Add the 2, you get 7. So x is equal to 7, and then you have to plug it in to find JK. So 2 times 7 plus 5. That's what you're seeing over here. So that's 14 plus 5. That's 19 for that. Okay, let's just do the last part here. They're giving us a lot of information, and this is going to be a little tricky simply because they have a lot of information and facts that you have to use to find this. So let's take a look. All right, so first of all, it says that these are tangents. So we right now know that they're equal to each other. Okay? What else do we know? We know that circle N has a diameter of 16. So that means I could put a diameter in here all the way across. That entire diameter length would be 16 there. P to Q is 3, so that's that little part there. And R to Q would be 12. Okay, so you can automatically see what the value of P to R would be. We already know what that one's going to be, right? That would be the 3 plus the 12. So that whole length will be 15. And likewise, if that whole length is 15, these are congruent, right? They're equal to each other. So this one is also 15, all right? So that gives us a little bit. Now, if you know that the entire diameter is 8, you also know that each of the radius lengths, so this radius and this radius, they are both going to be 8. So the radius lengths there are 8 for the big circle. And what else do we know? We also know that this is the center of the little circle. So that means then that this little length here and this little length are also both radiuses of that circle. And that little circle has a diameter of 8 there, which means this is 4 and this is 4. All right, let's see if we can answer any of these questions now that we have all this information. Okay, so PM. Let's find the length from P to M. Oh, we have that. P to M is my red segment there, and that was 8. Oh, no, not M. Sorry, that would be PM. PM, sorry, PM. That little tiny blue segment there. So that would be 4. Sorry, not 8. 8 is from P to N. P to M is 4. All right, let's find M to Q. M to Q. Now, that is this segment right here. You say, well, I don't have that length in there. But remember something. Every time you have a radius and a tangent, there is a right angle. So what you actually have inside here is a little tiny right triangle right in there. Okay, so I'm going to use that little tiny right triangle to come up with this answer. So I'm just going to create that little right triangle here so I can see it better. That's 3, that's 4, and again, I'm trying to find MQ. That is this right here. All right, so I'm going to use Pythagorean theorem to do that. 3 squared plus 4 squared equals x squared. So that's 9 plus 16, which is 25, and then you take the square root of both sides, and your x works out to be 5. Okay, x works out to be 5 there. So that is our length of MQ. So we have MQ is 5. All right, the next one they wanted to find was PR. We already found that one. That was 15. The next one after that was SR. Once again, we already found that because the two tangents are equal. The next one is NS. Now, I don't have an NS drawn in this picture, but I'm going to draw one in. And if you notice, that segment right there is a radius of the big circle. And remember what we said, every radius is the same length. So if this length is 8, this length is also 8. So NS has a radius length there of 8. All right, the last one we have to find is NR. Now, NR, again, is not in this picture. So I'm going to need to add it to the diagram. All right, so that is actually going to be from here to here. All right, that's NR. Now, what you are going to do is you can use either a right triangle on this side, because remember, a radius and a tangent makes a right angle. So you could use this right triangle here, or you could use the one on this side. Either one, these are both going to be the same right triangle here. So I am just going to use this one here. Okay, I'm going to use this one down here to be able to solve. And what I want to find is this length right here. So again, what I'm looking at is a right triangle. Looking at a right triangle where I have a side that's 8, a side that's 15, and I want to find the x value there. So let's plug it in. 8 squared plus 15 squared is equal to x squared. So that's 64 plus 225 equals x squared. So we have to add them together. We get 289, take the square root, and what you end up with is 17. That was a special, one of our special Pythagorean triples, the 8, 15, 17 triangle there. Okay, guys, I know that was a lot to take in. So we have a couple main rules that you really need to remember. First of all, let's just go back. Anytime two tangents meet at a point, they are congruent. The segments are equal. That's one of the main things we have in this section. We also have the fact that anytime you have a radius and a tangent intersecting, they form a right triangle. So you're going to end up with right triangles here. In this kind of question, remember, you were trying to figure out if it was a right triangle. But for these two, right, you had radiuses to tangents here. So you had right triangles to be able to figure out what your x and y values were. Okay? We also talked about these concepts of common tangent circles and common tangent lines. And again, I know that can be tricky. You might need to go back and rewatch that part of the lesson. And the final thing we talked about, of course, is circles that are congruent if they have the same radius length, okay? And, of course, concentric circles as well. It's just a circle inside of a circle. Okay, if there's any part of this lesson that you do not understand, just go back and rewatch. Okay, good luck, guys.